When railway barons mocked a revolutionary steam locomotive as a delicate iron skeleton, they were certain it would buckle before it ever broke records. Yet, in the cutthroat race for speed and profits, that very machine upended everything, shattering every locomotive speed record and shaking the industry's faith in brute force. How did a dismissed outsider's gamble threaten the financial lifeline of Britain's rail empires? The answer begins with the high-stakes numbers behind the speed war. Every tick of the railway clock carried a price. In the 1930s, Britain's trunk lines, LNER and LMS, competed not just for passengers, but for the Royal Mail's lucrative contracts. These agreements spelled out strict penalties. A flagship mail train running late could wipe out an entire day's profit. Performance clauses in the Anglo-Scottish mail contracts meant that repeated delays risked thousands of pounds in lost payments over a single season. The annual value of these contracts reached into the tens of thousands, a lifeline for companies squeezed by falling freight rates and rising competition from road and air. For traffic managers and finance directors, speed was more than a matter of pride. Each express service represented a balance sheet calculation. The fastest overnight trains didn't just carry mail, they filled first-class compartments and sleeping cars, the most profitable seats on the rails. Shaving minutes from the London to Edinburgh schedule meant more high-yield passengers, more sleeper surcharges, and more prestige for the company's name. While the fare tables rarely listed a formal express supplement, the reality was clear. The fastest trains attracted the travelers who paid extra for comfort, privacy, and time saved. Every acceleration on the timetable translated into higher average revenue per seat, sometimes by margins that could decide a route's fate. Railway companies tracked these numbers obsessively. Boardroom memos dissected the impact of a few minutes gained or lost. A missed connection could mean a cascade of penalties, not just from the post office, but from dissatisfied passengers demanding refunds or compensation. Company annual reports displayed passenger receipts by class, and the directors knew that a crowded first-class carriage on a record-breaking run could offset weeks of sluggish traffic elsewhere. The financial press watched these contests closely. Headlines celebrated new speed records, but investors looked for signs that faster trains were filling high-fare seats and protecting dividends. Share prices didn't leap on the news of a single record run, but they reflected the underlying struggle. Would the railway's investments in new engines and tighter schedules pay off in sustained traffic and profit? Each new express, each minute trimmed, became a test of management's ability to defend market share and keep the company's name in the black. Behind the scenes, contract tables and investor memos told a story of pressure and risk. The Royal Mail's punctuality clauses, the fine print of sleeping car surcharges, the nervous calculations of finance committees all set the stage for a technological gamble. In an era where every minute could tip the balance between profit and loss, the industry's appetite for disruption was growing. The numbers left no room for error and no patience for unproven ideas, until one outsider's radical approach forced everyone to recalculate what speed and survival really meant. Nigel Gresley's conviction stood in sharp contrast to the prevailing mood in British locomotive design. While boardrooms tallied risks and rivals added weight to their engines, Gresley returned from a trip across the continent with a different set of questions. On the Berlin to Hamburg line, he had watched the Fliegende Hamburger, a diesel-electric train, slice through the air with a grace and speed that steam engines rarely matched. The experience left him restless. He drafted a memo in 1934, lines of ink spelling out a new hypothesis. Weight is enemy. Cut what air does not need. Gresley's proposal called for a radical departure from the accepted formula of speed through mass. Instead of more tonnage and bigger boilers, he argued for a streamlined shell and a frame stripped of every unnecessary pound. The idea was simple: reduce resistance, both from the rails and the wind, and let the locomotive's power work more efficiently. The lighter the engine, the less energy lost to inertia and drag. Every ounce saved in the frame, every curve smoothed in the casing, could be turned into extra miles per hour without demanding more from the firebox or the crew. His draft outlined a prototype, a new class of Pacific, built not for brute strength but for minimum drag. The casing would be shaped by wind tunnel data, the boiler shortened, the motion streamlined. Even the smallest details, from valve gear covers to the angle of the smoke deflector, were chosen for their impact on airflow. Gresley's notes made clear that this was not just a stylistic exercise. He insisted that the locomotive skeleton be as lean as safety and steel would allow. Every hole cut in a frame, every lighter bracket, was justified by calculations from the drawing office. Skeptics in the engineering department circled passages in his memo, worried about stress, fatigue, and the unknowns of high-speed running. But Gresley pressed forward, presenting his case to the LNER board. He pointed to the evidence from Germany, to the numbers from his own papyrus trials, and to the competitive pressure from diesel sets abroad. The gamble was not just technical, it was commercial. If his theory held, the new locomotive would not only meet the speed demands of the day, but do so more economically, with less wear on the track and lower coal consumption per mile. The board authorized a small batch of prototypes, hedging their bets but granting Gresley the freedom to pursue his vision. The first drawings of the A4 Pacific took shape in the Doncaster works, each line reflecting the principle, cut what air does not need. As construction began, the railway world waited to see whether this lightweight theory would collapse under real-world conditions or deliver the speed that had eluded heavier machines. The stage was set for a trial that would test not only steel and steam, but the very logic of railway progress. Inside the trailing dynamometer car, the air was thick with tension and cigarette smoke. The instrumentation crew hunched over the chart recorder, eyes fixed on the slow crawl of paper as it fed through its mechanism. Precisely 24 inches for every mile covered. Each half-second, the clockwork timer dropped a black tick onto the roll, marking the passage of time with mechanical indifference. The linkage from the trailing axle drove the paper feed, calibrated and checked before the run. Its accuracy certified by the National Railway Museum as Artifact B123. As Mallard accelerated down Stoke Bank, the chart's inked line began to arc upward, translating steel and steam into a forensic record. Every half-second tick meant another 88 feet at 120 miles per hour, a blur in the real world, a measured increment on paper. The crew used a magnifier to check the spacing, cross-referencing the ticks against the milepost markers outside. Calibration was everything. A drift in the feed or a sticky clock spring could turn a record into an error. On this day, the system held. Once the run ended, the engineers gathered around the chart, measuring 5-second intervals to calculate average speeds. They found a sustained peak of 125 miles per hour with a brief spike, just a single second, touching 126. Gresley insisted on the conservative figure, knowing that every claim would be scrutinized. The chart, with its regular ticks and steady feed, became the final word, a hard, physical proof that could be checked and rechecked. Its numbers still cited in the museum's archive. For all the skepticism about lightweight frames and radical shapes, the record's credibility rested on this chain of measurement paper, clock, and calibration, each step documented and preserved. The heart of the A4's speed was not just its shape, but the metal it was built from. In the Doncaster drawing office, engineers weighed every ounce of steel, searching for the perfect balance between strength and weight. The main frames, once thick slabs on older Pacifics, were now cut from plate steel with a yield strength of 42,000 pounds per square inch, 10,000 higher than the standard 32,000 pounds per square inch plates used a decade earlier. This allowed the structure to be lighter without sacrificing safety, and every lightning hole, every rib, was calculated to carry just enough load. Stress diagrams from the period show how force flowed through the frame, bypassing areas that could be trimmed down to the bare minimum. But it was not only about the metal. AOM itself became the next adversary. At 100 miles per hour, air drag swallows more power than rolling resistance or gradient. The A4's casing, shaped by wind tunnel tests at the National Physical Laboratory, dropped the drag coefficient from the bluff 0.33 of a conventional engine to around 0.25. That single change saved hundreds of horsepower at top speed. The patent for the streamlined shell, filed as GB 4566789, specified the nose cone's rake and the smooth valances over the wheels, details that forced air to slip past instead of battering the engine. Together, high-strength steel and careful shaping let the so-called delicate iron skeleton resist stress and slice through the air. What looked fragile in the workshop proved robust where it mattered, on the rails, at speeds where every pound and every square inch of frontal area counted. Railway tradition said speed demanded muscle, more boiler, more cylinders, more weight on the rails. The numbers told a different story. The LNERA4 class, with Mallard at the front of the pack, tipped the scales just over 100 tons, lighter than the rival LMS Duchesses, which weighed in at more than 105 tons and carried up to 40,000 pounds of tractive effort. The LMS engines boasted heavier frames and bigger fireboxes, their designers convinced that mass alone would keep wheels gripping steel and schedules on time. Yet as Mallard's dynamometer chart traced its arc down Stokebank, the lesson was written in ink and speed. At 120 miles per hour, physics rewrites the rules. Drag rises faster than horsepower, and every extra ton becomes a penalty, not a prize. The A4's streamlined shell and careful weight discipline let it turn the same steam into more miles per hour, not just more tons hauled behind. Where the Duchess class put 70 tons on its driving wheels, Mallard managed with about 66, enough to hold the rails, but not so much that every pound had to be fought through the air. Tractive effort curves from the period show the paradox. Above 90 miles an hour, the advantage shifts from brute force to balance. Mallard's lighter frame and lower axle load let it accelerate where heavier rivals ran out of headroom, their extra mass wasted as heat and hammer blow. The so-called delicate iron skeleton did not just survive, it used less to achieve more, breaking records the heavyweights could only chase. The power-to-weight twist was not a fluke, but a recalculation of what speed truly required. Inspection foreman Henry Watts walked the length of the A4's new frame, clipboard in hand, every step echoing across the Doncaster shed. The engineers had finished their first set of high-speed trials, and now every inch of steel faced judgment. Under the harsh arc lights, Watts and his team applied MagnaFlux to the main stress points, axle boxes, horn guides, and the lightened web of the center frame. The dye seeped into microscopic fissures, glowing under ultraviolet light. According to the post-trial MagnaFlux sheet identification MW17, no crack exceeded 3 millimeters, well within the safe tolerance for high-speed running. Watts initialed the report, noting only a faint surface line near the right trailing axle, a mark that had not grown since the last check. The inspection log for July 5, 1938 recorded the result. No significant defects, frame integrity maintained at all tested sites. The anxiety in the workshop faded as each reading was confirmed. The so-called delicate skeleton had passed its first ordeal without a single structural failure. Engineers gathered around the inspection bench, trading quiet nods as the final sheet was filed. The locomotive's frame, lighter than any Pacific before it, had withstood stresses that would have exposed any hidden flaw. For the skeptics in the boardroom and the men on the shop floor, the evidence was now on paper. The A4's iron skeleton was not just theory, but proven strength ready to face the next challenge. Depot superintendents faced a new kind of headache when the streamlined A4s entered service. The sleek side valances and flush casings that cut through air at 100 miles an hour also blocked easy access to valves, pipes, and motion gear. Routine jobs, like lubricating the conjugated valve gear or checking axle boxes, now called for extra steps. Shop Hour Comparison Sheet DS42, circulated in October 1937, showed a sharp jump. The A4s demanded 18% more labor hours per overhaul compared to their older open-framed cousins. Time spent removing and refitting the streamlined panels piled up, turning simple inspections into drawn-out procedures. Cost accountants flagged the problem in quarterly reports, calculating that each A4 overhaul cost dozens of extra man-hours and tied up scarce, skilled fitters. In the Doncaster works, the tally of maintenance hours per engine climbed steadily. The streamlined casing, so brilliant on the main line, became a source of friction in the back shops. Some managers argued that those extra hours in the depot ate away at any savings from higher speed or fuel efficiency. For the men on the shop floor, the A4's beauty came at a price. One measured not only in steel and steam, but in overtime slips and crowded maintenance bays. The debate over cost and complexity echoed through the boardrooms, feeding doubts about whether the new design could ever become the railway's standard. Each extra hour in the workshop was another reason for traditionalists to resist change, even as the A4s racked up headlines out on the rails. Within a year of Mallard's record, the British locomotive industry found itself in a new race to imitate what had once been ridiculed. At Crewe, the London, Midland, and Scottish Railway ordered a series of streamlined engines called the Coronation class. The first of these, rolled out in 1937, carried a casing shaped by wind tunnel experiments and a frame drilled for weight savings, a clear echo of Gresley's approach at Doncaster. The official LMS specification sheets for the Coronations show a shift in priorities, lighter platework, smoother noses, and attention to drag coefficients that had been dismissed as theoretical only months before. Patent filings tell the same story. In the 12 months following Mallard's run, the British Patent Office received a surge of applications in Class 104295 for locomotive bodies and streamlining. Diagrams in these patents reveal not just new shapes, but new ways of mounting fairings, venting smoke, and balancing frames for high-speed running. The technical press began to track each new design as a potential challenger, and boardroom minutes from both LMS and GWR referred directly to the need for streamlined express types to remain competitive on headline schedules. What had been an outlier became the new standard. Within 2 years, even conservative workshops were producing engines with swept casings and lightened frames, and the language of aerodynamic efficiency entered official procurement documents. The industry's center of gravity had shifted. Speed now meant streamlining, and the old logic of mass and muscle gave way to a new orthodoxy of weight, drag, and measured advantage. Today, high-speed trains race across continents, each built on principles once dismissed as impossible. As rail networks face renewed pressure to cut emissions and increase efficiency, the lesson endures. Real progress demands questioning the weight of old assumptions. Innovation rarely looks sturdy at first glance. Sometimes the future arrives on rails that everyone else thought too fragile to last. What risks are we still afraid to take?